Uh, Dr. Cole has authored two book chapters and published 50 journal articles, including papers in Science, Nature, Nature Physics, Nature Photonics, Nature Nanotechnology, Nature Communications, Physical Review Letters, and the Proceedings of the National Academy of Sciences. Uh, Leveraging his expertise in micro and nano fabrication, tunable semiconductor lasers, and cavity optomechanics, together with Professor Marcus Appelsmeyer, Dr. Cole founded Crystalline Mirror Solutions, an international photonics startup commercializing high-performance optics for laser-based metrology and manufacturing systems. CMS was successfully acquired by Thorlabs Incorporated in December 2019, and it's been rebranded as Thorlabs Crystalline Solutions, TCS, adding high-performance crystalline coatings to Thorlabs' ever-growing product portfolio. With that, I turn it over to Dr. Cole.
Yeah, thank you very much, Russell. That was a very in-depth introduction, so hopefully that covered everything. Let me share my screen. Hopefully you can see the slides now.
We've got your screen now.
Can you see it?
Yes, we can.
Okay, perfect. Yeah, so as Russell mentioned, I think many of you coming from an optics background are probably familiar with Thorlabs. We're an interesting new group operating out of Santa Barbara, California, whereas the primary location of Thorlabs is in Newton, New Jersey, with a large semiconductor fab near Baltimore and Jessup, Maryland. So I'll give you some background on kind of the niche stuff that we do in Santa Barbara, show why this is interesting and why it's sort of a new item in Thorlabs' ever-expanding portfolio of products. Yeah, for background, we are essentially like a high-end coating house, but rather than doing direct deposition via typical physical vapor deposition processes such as evaporation or sputtering, we operate with a really unique merger of semiconductor materials and microfabrication techniques with bulk optics. I'll make that clear in the course of the presentation, and that'll be kind of a recurring theme that'll come up, multiple times here. So jump right in. These are the points to be covered. This is effectively the outline, but the key points I want to get across today. So I'll give really quick background and timeline on crystalline coatings. The nice thing is Russell gave such an extensive intro that most of that is covered, but I'll touch on it still. I'll then give a very quick, recap on the basic market and for optical coatings in general, and give a little description of just basic mirror technologies and just comparing various techniques. And then I'll dive deeper into our substrate transfer crystalline coatings and give you a little bit of an overview of just how these are made, because it's a very different manufacturing process than typical physical vapor deposition derived coatings. And then I'm going to highlight two sort of case studies or two key application areas. And this is, we tend to focus on, just given the properties and performance metrics of our mirrors, optical metrology space. And so I'll give an overview of two application areas in near infrared precision measurement, and then mid infrared based trace gas detection or cavity ring down systems. So hopefully you learned something new today. I'm very happy to see it's really well attended. This is actually the first time I've participated in an OSSC event. So again, thank you very much for having me, and I hope you enjoy the talk. So, I said this right at the beginning, we operate at this very unique intersection of compound semiconductor materials and bulk optics. And you do see, sort of overlap or cross-pollination between these fields already. Let's say people borrow deposition techniques such as atomic layer deposition or CVD techniques from the semiconductor field, or various metrology tools will go back and forth. And this, I think, will be another example of that. We're taking semiconductor materials and microfabrication techniques, which of course have their root in integrated circuit manufacturing from many decades ago, And we're using that to make really high-end, premium optics. And for us, it's a choice of materials, and I'll show why that's interesting to exploit these 3-5 compound semiconductors. But then we leverage highly like the existing infrastructure, both from the semiconductor side, but even more importantly, in just making super polished, really high-end optics. It's really nice. We're pretty local in that sense on the bulk optics side. So I do want to highlight the folks at Coastline Optics that have been extremely supportive for us, especially when we were a tiny little growing startup in Santa Barbara. It was really nice having them, local to us in Camarillo. So thanks to John, Dennis, Mark, Jean, and the crew there at Coastline. Again, as Russell highlighted, I had did a stint in Vienna, Austria for about 5.5 years. And this work is really a spinoff of the work that was done there. So I came from a MEMS background, so micro electromechanical systems, where like it was mentioned, I was making tunable laser devices. And these tunable lasers had a moving Bragg mirror that was a gallium arsenide aluminum, gallium arsenide based mirror, just to directly change the cavity length and tune the laser. It turns out in those kind of systems, if you have some sort of moving element in an optical cavity, you can see directly radiation pressure effects or optomechanical coupling, I'll call it in general. I'm not going to go into that in more detail in the course of the presentation, but just want to point out that that's an entirely its own field of study. But in the work I was doing, it was more engineering focused, trying to make better, microfabricated, integrated tunable laser systems. But as I said, we had this moving mirror, and if you pump this thing hard enough, you could, DC deflect the mirror, or you could modify the dynamics of that vibrating mirror. And as a side note, I noticed there were a bunch of physicists in the sort of early 2000s, let's say 2004, 5, 6 timeframe, that were investigating that in detail. Like, how can you use this as a platform to do some very interesting physics experiments? Most of them were using dielectric materials. So pick your favorite, like titania silica or tantalus silica, to make their movable mirrors. Whereas I was doing compound semiconductor devices because I was making VCSELs, like these integrated laser structures. And it turns out there were a lot of really interesting advantages if you use direct single crystal compound semiconductor materials in that niche, cavity optomechanics space. The mechanical Qs, which is something I'll go into, mechanical quality factor, I'll go into more detail later, can be extremely high, which means that with a high finesse cavity, so high optical quality and high mechanical quality, you can really drive some interesting dynamics in those systems. And that is in strong or stark contrast with the dielectrics, which can have good optical quality, obviously, like an ion beam sputtered silica tantalum multilayer. But they have poor mechanical properties. Again, I'll explain what I mean by that, by poor mechanical quality factors later on. So that basically brought me to Vienna. We're focused solely on that. It turned out there was a bunch of metrology folks that wanted very low noise mirrors. Again, I'll explain quantitatively and qualitatively what that means for low noise mirrors. For precision measurement systems, things like LIGO or cavity stabilized laser systems for optical clocks and things like that. So yeah, we basically leverage this existing infrastructure in semiconductor-based materials like gallium arsenide aluminum, gallium arsenide, and then most of our team comes from a semiconductor background. So we do standard lithography, etching, and so on to define the coating, and then basically transfer it to the final optic. I'll go in much more detail with that later on in the presentation, but this is just to give a flavor of where it came from. So going from the tunable lasers to these freestanding optomechanical resonators to taking these and turning it into a real coating. Here it was a freestanding 50 micron mirror, but now we need to scale up to centimeter inch scale mirrors. So the timeline goes back, it's a fairly new technology as far as optical coatings go. I'll make that clear in a few slides, but begins with early work at Lawrence Livermore, postdoc that I did there. And then as Russell mentioned, I moved to Vienna and really pushed the work much farther there, more in the microfabricated version of things. And then initial contact with LIGO really drove trying to scale this up, trying to go from freestanding 50 micron mirrors to a coating transferred onto an arbitrary substrate. And the company Crystalline Mirror Solutions was founded in 2013, originally in Vienna. For need of manufacturing capabilities, I moved back to Santa Barbara in 2014. Ended up having a multinational startup, so we had locations in Austria and California. I do not recommend that to anybody. Small company's hard enough, and a multinational startup is insanely challenging. But it was fun. We could, leverage funding schemes in Europe and in the US and so on. And yeah, then from the period of 2014 until now, it was just making, evolutionary improvements in the coatings, pushing to lower absorption, lower scatter, and so on, until in 2019 we were acquired by Thorlabs. And we still operate out of Santa Barbara, our same office and lab space there. And we still continue to do our niche products, which are these semiconductor super mirrors or crystalline coatings. You can buy them in the catalog now. That's a big difference compared to what it used to be, right? We were making just custom runs for folks. So yeah, this is not trying to be a marketing push, but it's fun to see the evolution of the technology. So I am not an optical coatings expert in terms of the business side of things, but I will just briefly touch on, at least from my perspective, what the basic sort of market outlook is for optical coatings. There's a very large spectrum of providers here, right? You have manufacturers doing a variety of solutions. Almost all of these, or at least what I'm going to focus on, are going to be vacuum-based physical vapor deposition. So I'm not going to be talking about sol gel or other liquid phase processes. And this can obviously span everything from evaporation through various sputtering techniques. Obviously, there's a large variation in quality there, and that's clearly going to be process and materials dependent. And in that tier, we are I would say, almost super premium offering, right? So if you have ion beam sputtering as the gold standard of dielectric physical vapor deposit coatings, we'd be equal to that or even a rung above. So that's both going to impact the cost of our optics and also the performance metrics that we're targeting. Given that, our typical customers include either academic experts at, pick your fancy school and probably working with them, or it's going to be a metrology lab. NIST or GILA in the US, PTB in Germany, NPL in the UK, CERT, and so on. The NIST of whatever country is likely one of our customers. So yeah, it's an interesting niche. It tends to be high value, but low volume, to make it clear there. And we do have some industrial partners, some defense contractors, or I'll highlight a company here, Menlo Systems, that I'll point out some more details on later. So that's it in a nutshell. In this sort of spectrum of coating technologies, we are going to be a premium offering, pushing just the lowest absorption, lowest scatter, highest performance possible. So now I'm going to jump way back, and I think for most people this is going to be very basic, but I'm just going to give an overview of mirror technologies. So there's two main classes of thin film reflective optical coatings. The simplest is going to be just single layer metal mirrors, right? So this could be silver, aluminum, or gold with or without a dielectric protection layer. You can get relatively high performance in these, let's say reflectivities at the 93 to 98% range, but there's some major drawbacks. So one, you're not going to be able to transmit light through the metal. It's opaque, obviously. Your reflectivity is going to max out at something in the high 90% range. So you're not going to make a high finesse cavity out of this. And due to some of those facts, like the intrinsic absorption, your laser damage threshold is going to be somewhat limited. So if you want to push, if your aim is to make a high reflectivity mirror beyond what you can achieve with a metal, then you're going to switch to a dielectric structure. And really the basic fundamental difference is the fact that the the component or constituent materials that make up that mirror are transparent, right? Whereas the metal is absorbing and is reflecting based on the fact that you have these electronic interactions. Here you're relying solely on Fresnel reflections in a transparent medium. So if you use a properly designed interference coating, you're going to get lower losses just given the fact that it's non-absorbing. And if it has a nice sharp interface and smooth surface, you can reduce the scatter. So let's go a step deeper into the interference coating structure. So this is a plot of refractive index as a function of distance or position in the mirror or in this multi-layer. This can go on to near infinity, say many periods terminating on the substrate, but I've cut it off here. And if you have light incident from the left, if you've designed, like in this example, a simple Bragg mirror, so a bunch of quarter wave alternating high and low refractive index materials, you'll see an exponential decay into that mirror structure, and you'll see a strong counterpropagating reflection there. And again, the point is these individual materials are transparent, and you have these sort of weak Fresnel reflections at each interface, but these will constructively interfere and add together to give you a high reflectivity at the so-called Bragg wavelength. There are three loss mechanisms here. So the first is going to be transmission, and this is a design parameter, right? So you will say tune the refractive index difference between your high and low index materials, and you'll design out the number of layer pairs you want to hit your target transmission value. Transmission, the other way to think about it is leakage through, the output side of the mirror. So that's, again, it's something you're going to design in, and they'll have these two excess loss parameters, the absorption and scatter. They're pretty obvious given the name. I'll go into more detail a little bit later, but basic idea absorption is going to be you have either defect states or you're illuminating above band gap or some sort of process that gives you absorption of photons into the structure, and scatter is going to be due to some imperfect surface, right? You have a wavefront error, or you have micro roughness, or you have interfacial roughness that scatters photons off axis or off the direction that you want. Primarily here, we're going to be focusing on minimizing the absorption and scatter. So we want high purity, relatively wide bandgap materials, at least for the wavelength range that we're operating in. And we want to reduce the scatter by making very smooth surfaces with sharp interfaces, good control over surface figure and so on. So that's the basic overview of the mirror structure. Now we're going to show a really select, simple timeline of optical coatings. I'm missing lots of processes here, but it's kind of fun to think about that there's a long history behind optical coatings. The first coatings were made by arc evaporation in the mid-19th century, then progresses to evaporated coatings in the early 20th century, and then you have the advent of, I'd say, high quality thin film structures developed deposited via sputtering processes in the mid 20th century. And again, in terms of these physical vapor deposited structures, the gold standard would be these ion beam sputter films developed by Litton Industries for their ring laser gyroscope product line in the mid to late 1970s. I'm putting this out here just to show that ion beam sputtering technique gives insanely low levels of loss, high performance, which I'll highlight. But it's a very mature technology, right? You have 40 years of experience here. Our crystalline coating technique is much newer. So this was first demonstrated in 2012, and we've been trying very rapidly to catch up or even exceed what can be achieved with ion beam sputtered coatings. So newer is not always better, obviously, but it's our aim to leverage the unique aspects of these semiconductor materials as passive optical coatings, and I'll go through that in detail today. So, I'm not an ion beam sputtering expert, but give a quick overview here. So, state-of-the-art multi-layers are typically alternating high-index tantalum penoxide with low-index silica. And this is usually deposited as shown conceptually here. You have ionized beam of noble gas atoms impinging on a target. The target could be directly an oxide, or it could be a metallic target in an oxidizing environment. And you effectively sputter atoms off of that surface and have them adhere to your final substrate. If you can get good surface quality on that polished substrate and guarantee good adhesion between the deposited films, you can get excellent surface quality. Angstrom level RMS roughness, which gives you optical scatter at the ppm level, and subpart per million absorption, just due to the high purity, wide band gap of these metal oxides. So it's a flexible technique in terms of the substrate material choice, or even topography or figure of that substrate. It's scalable in terms of manufacturing. You can load, as long as you have good uniformity in the chamber, you can load a number of substrates. But there are some disadvantages. These materials don't tend to operate at long wavelengths, so you're going to have a cutoff maybe 3 microns or so. Thermal conductivity is relatively poor at the sort of 1 watt per meter Kelvin level. And as I mentioned, they have high elastic losses. This will be hopefully the new physics you learned today, which is Brownian noise topic. It's very niche, but something very interesting. And these glassy materials tend to show very high elastic losses. That is the imaginary component of the Young's modulus, which I'll go into in more detail later on. This tends to be high in these materials. And so there are application areas that need alternatives to ion beam sputtering. And so how can we exploit our alternative materials, such as the semiconductors I've been talking about, or others that may not be amenable to direct deposition as performed via ion beam sputtering or other physical vapor deposition techniques. So interestingly, at the same time that Litton was developing their ion beam sputtering process, Bell Labs, there was a group, von der Ziel and Illigums, 2 guys that had done the first single crystal semiconductor-based interference coatings. These were gallium arsenide, aluminum arsenide multi-layers, which initially I think was simply a novelty. I actually don't know the background or what the intended application was. but it ended up finding use in these so-called vertical cavity surface emitting lasers, which is a field that I come from. I think many of you are familiar with these, but if you're not, this in cross section is an interesting microcavity laser structure where you have two interference coatings or two high reflectivity Bragg stacks with a very thin gain region in between. So it's a relatively high finesse cavity for a laser. The laser light rattles around between those two Bragg mirrors and emits normal to the surface of the wafer. So you can make really neat, linear two-dimensional rays of these lasers, test them on wafer. There's a huge commercial market behind these now for facial recognition in smartphones, for optical mice, for short-range networking applications. The VCSEL market is approaching $4 billion now, which is really incredible, especially somebody like myself coming from that field when it was much smaller, about 20 years ago. So obviously, these single crystal interference coatings have found a lot of nice uses in integrated optoelectronics, but you don't see them in general optics applications. And the major limitation is the fact that it's a single crystal structure, which requires crystal growth, and so you have very severe constraints on substrate selection. You need to meet the so-called lattice matching condition, which means your interatomic spacing and crystalline symmetry needs to be the same. So you can't choose an arbitrary substrate. Obviously, you can't choose a glass, to deposit on it. So this is a very busy plot I'm going to spend about 10 seconds on, but this is sort of near and dear to my heart. UC Santa Barbara has this very nice compound semiconductor focus, at least in the materials department and electrical engineering. So this is a plot you see a lot from Herb Kromer, Nobel Prize winner, UCSB. So this band gap energy is a function of lattice constant for a variety of these compound semiconductor materials. These are group 3 of the periodic table combined with group 5 of the periodic table. And you can effectively say that refractive index will scale with the band gap. And so if you want wide index contrast, you need a large separation in band gap energy, but you need to find compounds that also have a matched lattice constant or interatomic spacing, and that is few and far between. But nature gave us this really interesting combination of aluminum arsenide and gallium arsenide, which is effectively lattice matched sort of right out of the box. So, large band gap contrast, large index contrast. And so you see this, like I said, in VCSELs and a number of applications. It is like the premier semiconductor heterostructure multilayer. So that's what we're working with, just given the fact that we can lattice match these and get high index contrast. Now, to get around this lattice matching constraint, we need to develop a new technique. Otherwise, we're stuck just with planar gallium arsenide. So what we do is we leverage all this background or existing infrastructure in integrated circuit or microfabrication, lithography, etching, everything you use to make a VCSEL or other structures, and we combine these with these beautiful precision polished optics. And combined together, we end up with our crystalline coatings. So there is little new in terms of the multilayer itself. So this is a high index gallium arsenide layer, has a refractive index of about 3.5, 3.3 to 3.5, depending on the wavelength. And low index aluminum gallium arsenide, it's a ternary alloy to avoid oxidation. I won't go into more details there. Refractive index of about 3, 2.9 something. And we use standard epitaxy techniques to grow the multilayer. I'll touch on that in a minute. So this looks just like the work from Bell Labs in the mid 70s or anything, this is a part of a VCSEL, if you want to think about it that way. The big difference we do though is, we use, again, lithography, selective etching to define the lateral area of the coating. And then we effectively, I'll claim, lift it off, but I'll show more detail in a minute. And then we take that coating disc and stick it on the final substrate. That's a direct bonding process, so there's no adhesives or solder or glues of any sort. If you come from an optics background, we're basically optically contacting the coating onto the substrate. If you come from a semiconductor background, we're using wafer bonding to stick the semiconductor onto the substrate. And one of the key advances that I developed was the ability to do this on a curved surface, which is somewhat challenging. So yeah, that's basically what we do. And I'll go into more detail on that in a minute. I'm going to give a shout out to Mark White, who was our sales manager at Crystalline Mirror Solutions and is now OEM sales for Thorlabs Inc. Mark had a really nice point here that I should highlight some of the interesting aspects or little quirks of crystalline coatings. So one interesting thing is our coating can be saved later, right? It's like you froze the deposition process. Because we separately deposit, we can keep portions of the wafer and run it later, right? So we can save that run. The other thing is we can qualify the coating before we ever touch the substrate. So we can do epitaxy, pull it out, measure absorption via PCI or other processes, measure scatter, measure the transmission, whatever we want, make sure the coating qualifies, and then go start, incorporating it onto the substrate. Because we use lithography and these semiconductor-based dry or wet etching processes, we can get, micron or even sub-micron scale, lateral positioning or dimensional accuracy. That's the beauty of semiconductor manufacturing. It's just so well developed. Our materials have a very wide transparency window. We cannot go short. I'll make that very clear in the course of the presentation. Gallium arsenide has a band gap from about, let's say, 900 nanometers at room temperature, but it goes very long, out to say 12 or even 14 microns. It's a good mid-IR material, which I'll make clear today. Other advantages are we have very low absorption. Our K values are 10 to the minus 7, 10 to the minus 6, again, on par with the best ion beam sputtered films. Refractive index is fixed by composition. This is very interesting. Our refractive index is basically set by nature, not by the deposition chamber, because it's a stoichiometric crystal, let's say in the case of gallium arsenide. Also, our stress is very repeatable because it is driven by the interatomic spacing. So the lattice, sets the stress for us. So it's usually 130 megapascals compressive every time. We can also engineer that if we want by using ternary alloys to reduce it, but typically we just live with the 130 megapascals. It's fully dense. There's no narrow absorption lines, no water absorption, because again, it's a single crystal. It's as dense as you're going to get, right? And very low elastic losses, which goes into this Brownian noise topic she'll show. So I think this is just highlights some of the differerences, some of the interesting aspects of our technology. So, our manufacturing inputs are as shown here. We start with a gallium arsenide base wafer. We just buy these from there's a few vendors that'll sell these, grow big boules, cut them up, polish them, and that's our seed for crystal growth. For deposition, we use molecular beam epitaxy. I'll go into that in a few minutes. And then we leverage all this, microfab and bonding processes. So we have little fixtures that do small parts, and we have a large wafer bonder that'll bond up to 20 centimeter optics for us. And I highlight all these because, inputs on some of this will, if you were to move to say large areas for say LIGO or others, it gets very challenging to get these large seed crystals or highly uniform epitaxy and so on. But so that's our inputs compared to say a sputtering chamber, which is different. So as I mentioned, for the crystal growth, we use molecular beam epitaxy. This is also very, say, tried and true technology. This is what von der Zyl and Illigums were using in the 70s at Bell Labs. This is a 50-year-old technology. It's basically high temperature evaporation. You have a high vacuum chamber, say 10 to the minus 11 torr or so. You hold your substrate at quite elevated temperature. 600 Celsius is sort of a typical range for the arsenides. And then you have these effusion cells, Knudsen cells, whatever you want to call them, with high purity elemental materials. So in our case, aluminum, arsenic, gallium, could be indium or phosphorus, depending on what you're doing. And you basically mechanically shutter these things. They're heated, so you have a beam of atoms just going off into the vacuum chamber, depositing on that high temperature substrate. That high temperature allows the atoms to diffuse around, find their spot on the lattice, and continue to template off that base crystal. You can get beautiful atomically sharp interfaces. This is a TEM image I stole off the internet from Cambridge. And you can alternate these materials, and it's a distributed single crystal, which is really fascinating to think about. High purity, sharp interfaces, everything you want if you really want to push the limits in terms of performance for an optical coating. Production tools can be quite large. Like if I go back a slide, that's a large production MBE chamber. That's an office chair in the corner for scale. So you can do 14 by 4 inch wafers, 7 by 6 inch wafers, or 3 by 8 inch wafers in those systems. I will now step through the manufacturing process. It's just more interesting, I think, to show it off. So we typically deposit on 6 inch or 15 centimeter diameter wafers. And I'm going to show an example of making 2 inch optics out of this. So we can punch out or etch out basically 4 coating discs that are roughly 2 inches in diameter. I think these are 48.8 millimeters for this example. And then we have some little witness pieces, these little centimeter scale witness pieces that we're going to punch out of that. Again, we use lithography. It's a 2-stage process here I won't go into to etch and define those coatings. And then I'm going to flip into cross section here. So I have my thin epitaxial, single crystal multilayer epi structure there sitting on top of my handle wafer. I'm going to use lithography and etching to define the coating shape. I'm then going to etch deeply into the substrate, And this is where single crystals do some weird stuff. So you can see some strong anisotropy and etching there, right? What's kind of neat though is we get this nice vertical wall, which then sort of tapers off by some crystalline plane that for whatever reason wants to etch a little slower, and then down to this flat base here. And now it's going to be animated. So watch in the upper left as I click, we're going to lap or grind back through the structure. And we're now going to cut into that trench that I etched. So I'm going to pop out those 4 2-inch discs in those little witness pieces now. And then I'm going to take that little coupon, that little coating disc, and I'm going to integrate it with the final substrate. So in this case, it's a 24 millimeter thick fused silica substrate, concave radius of curvature 5 meters on the surface there, and again roughly 2 inches in diameter. This part was made by Coastline Optics to keep to keep plugging them. That substrate is loaded into our custom bond fixture. We have these mechanical flags. We also have options to do pneumatics or sort of vacuum holding. But in this simple case, these flags or spacers hold the coating disc up off the substrate surface. We load this into our vacuum chamber, push down, initiate the bond wave or initiate contact in the center. As the bond propagates out, we pull the spacers and let the rest of the coating drop. That's how you bond to a curved surface. You gotta make controlled contact in the center first. So that's the basic overview of how it works. Again, it's an interesting technology. So separate crystal growth, lithography to define it, cleaning everything, right? Because we're bonding and we don't want any particles and so on. And then prepping the surface properly and then pushing it into contact. So again, optically contacting the coating with the substrate. We would then do a final selective substrate and etch stop removal process and leave the coating on the surface of that optic. So here's a nice photo of a little lineup of optics there, various geometries of the coating, various substrate materials. So we can successfully coat fused silica, silicon, silicon carbide, sapphire, you name it. Continuous maximum coating diameters at 20 centimeters. That is the largest gallium arsenide wafer you can buy right now. It's 20 centimeters or colloquially 8 inches. To go beyond that, you need to get custom grown crystals, which gets very expensive. So let's call it 20 centimeters for now. The tightest curvature we bonded to is a radius of curvature of 10 centimeters, which is strong. You can clearly see that by eye. Getting tighter than that, it becomes kind of a cartography problem. You know, you're taking a flat sheet and trying to warp it in 2 dimensions, and it starts to buckle around the edge. So the stresses are actually quite low. It's not a fracture problem. It's a warping, buckling problem in that case. Our optical losses are quite good. So on par with the best ion beam sputtered coatings in the near infrared. So we're looking at, and the best optics we've made to date, scatter on the order of 2 parts per million or 2.5, let's say, and absorption down to the tenths of a ppm. So I don't know, 0.1 to 0.5, let's say, in our best optics. So we could do cavities with linear cavities with a finesse in excess of 500,000 in the 1 to 2 micron range, no problem. So like I said, comparable to what you can do with a good optimized ion beam sputtering process. So that's just an intrinsic component. Then there's 3 main advantages beyond that, beyond the high optical quality. So one is this ultra low Brownian noise, this low elastic loss issue, which I'll explain because I know most of you have no idea what I'm talking about when I say that. We can achieve IBS levels of performance out into the mid-IR. And this is something very new for us. But recently, and just last week, we published a paper where we measured absorption at the 7 part per million level. Microns, which is completely
dropped out.
Absorption, right? We're 7 parts per million.
It's back.
Oh, sorry. What point did it drop out? I'm sorry.
It froze right when you were saying we published 7 parts per million.
Yeah. So sorry about that. Yeah, thank you for interrupting me when it does that. So yeah, the comparable evaporated or sputtered coatings will typically give hundreds of parts per million, even up to 0.1%, right? So that's for high quality mid-IR coatings. So it's a new regime, I would say, for mid-IR coatings, the first super mirrors in the mid-IR. And then finally, I won't go into more detail here, but because of the crystalline nature of the materials, the thermal conductivity can be quite high. So we're looking at about 30 watts per meter Kelvin through thickness, which is interface limited, just phonon scattering off the interfaces. And in plane, something on the order of 70 to 80 watts per meter Kelvin. And that can lead to some relatively high damage thresholds for CW or quasi-CW systems where you're thermally limited. So we've pushed optics up to 64 megawatts per square centimeter with no damage. I would be very happy to find partners that can give me 100 or 200 megawatts per square centimeter, because I would like to damage one of these optics in CW and have that number finally. So now I'll focus on the Brownian noise topic. So, this is the what we call our crystal stable optics line. And so these are primarily used in ultra-stable reference cavities for very narrow line width lasers. These are large passive etalons with our end mirrors that are used for generating very low millihertz line width lasers. And I'll show more details on that. These are usually used for frequency references, for clocks, for various applications like that. And then we also do some R&D for future gravitational wave detectors, which are also limited by this same effect. So, the most precise measurements of time and space are shown very briefly on the slide here. You have these optical atomic clocks, either trapped single ions or lattice of cold atoms that you're going to probe, and that is effectively your pendulum of your clock. Nature gives us these atoms that have extremely narrow line widths, millihertz or sub-millihertz line widths on some of these transitions. That's a very good oscillator. But ideally, you need a laser to be, you don't want to be limited by your laser, but rather by that natural line width of that atom. So you want to push that laser to be as narrow as possible. And it turns out that these systems are actually limited by the Brownian motion of the optic, which I'll show in a minute. And on the spatial measurement side, you have these gravitational wave detectors, which can achieve this phenomenal levels of sensitivity. 10 to the minus 18 meters displacement resolution over 4 kilometers, which is just incredible. This is strains at the 10 to the minus 22, 10 to the minus 23, pushing to 10 to the minus 24 delta L over L. And they're also directly limited by the Brownian motion of the optics. We normally think of Brownian motion as like a pollen grain in the fluid or like an atom trapped somewhere, but no, this is a bulk object, and you're limited by its thermomechanical noise or Brownian motion. So we have shown, proven low Brownian noise performance, and this really is just owed to the single crystal nature of the materials. Basically, you have low elastic losses. I'll go into more detail in a minute. And so if I take one of these etalons or reference cavities, so this is again, a large linear cavity. Click on chat to make sure everything's okay. I'll get to the questions later. So the early cavities were made from ultra low expansion glass spacers, so for zero thermal expansion, and then ultra low expansion end mirror substrates. But it turns out people at the time didn't understand that it was actually the Brownian motion was driven by the high elastic losses. A couple folks noticed this, pointed out you need to push to the lowest elastic loss possible in the materials, change those ULE end substrates out for fused silica, and all of a sudden you have a large drop in noise. So I'm looking at the plot to the left, which is the total noise as a function of material selection, I'll call it. And we've color-coded the noise contributions from the different components. And so spacer being black, coatings being red, and substrates being, or substrates black, sorry, coatings red, spacer blue. So fused silica made a big advantage just given its higher mechanical Q. And then finally, there have been these cryogenic systems developed, either sapphire or silicon, where you have extremely high mechanical quality factors, and now you're solely limited by the coatings. By just the Brownian motion induced by the low elastic or the high elastic loss of the coatings. Crystalline coatings show a significant reduction, and this was after something LIGO and some of these groups have been looking into for a couple decades. So that was a very exciting advancement. 10 times elastic loss reduction at room temperature and up to 100x at cryogenic temperatures. Click here. So there's a lot of noise sources. I'm going to be focusing solely on Brownian noise in these cavities, and that is just the intrinsic thermal fluctuations, so quantum temperature, fluctuations in the material that drive mechanical motion of the body. That's the best way to think about it. And I'm just going to jump to the next slide. For those of you who love math and equations, I just wanted to show if you're a noise person, this is the mean square fluctuations at a finite temperature. So 4 kT, that's just energy, right? Boltzmann constant temperature divided by the radial frequency squared, and then multiplied by the mechanical admittance. Okay, so this is if you push on something, it's the ratio of the velocity resulting from that applied force. If you look at the standard mechanical admittance expression here and then plug that in, then you get the mean squared thermal noise of a mechanical body. I'm not an electrical engineer, but for those of you who may be, this is the same physics as Johnson noise in a resistor. So an object that has a finite resistance will have a finite electrical noise. This is the mechanical analog of that, if you want to look at it that way. So in this expression at the bottom, again, you have energy scaled with the radial frequency. And then you have this phi, which is the elastic loss. This is the imaginary component of the Young's modulus. So we all know Young's modulus is the stiffness of a body, but what we don't know, or what we don't typically think about, is there's a phase lag. If you take a rubber or viscoelastic solid and you push on it, of course, it takes some time for it to respond, but everything does that. Diamond does it, right? I mean, the hardest materials you can think of, you push on it, there's a slight phase lag, but it's so small, we typically totally ignore it. But in this application, it's really going to be important. So that's something new that you can learn today. Everything's soft, everything's viscoelastic at some level, right? So if I take that reference cavity, which I'm showing here in cross section, this thing consists of a spacer, that rigid body that holds the two mirrors at some separation. And I don't need to hold like a controlled, ultra precise distance between the mirrors, but I just need to hold them rigidly, let's say that. And then the end mirrors consist of a substrate upon which I've applied the coating, which is shown in orange there. If I inject light in, I excite some resonant mode, and that light bounces back and forth between those two mirrors. Ideally, if this thing was at 0 Kelvin and very still, I would have a perfect frequency reference, right? Just limited by the line width of that thing. But in the real world, this thing is constantly moving, right? It's sitting at a finite temperature, so that spacer's expanding and contracting, the substrates are moving, even if it's ULE, right? Even if it has zero expansion, even if I do the best job I can to hold the temperature to exactly the temperature I want, there are intrinsic thermal fluctuations that we can't get rid of. So it is this intrinsic Brownian motion that drives the length instability of that cavity. And here's where I'm going to teach you something new. So actually the magnitude of that motion depends on the imaginary component of the Young's modulus of the material, right? Which is really strange. Like we think of Brownian motion, typically we think at a given temperature, I'm going to have a given, amount of motion, but there's a shape to the frequency response that controls that. So here, if I plot the total noise of one isolated mechanical resonance of that body, maybe it's the breathing mode of the spacer, maybe some flexural mode of the substrates. So I'm going to take that one mechanical resonance and I'm going to plot its noise, basically its amplitude of deflection as a function of frequency. So if you've ever done mechanics, you've seen these Bode plots or these, kind of roll up to resonance and roll off. But now what I'm going to do on this plot is I'm going to change the mechanical quality factor of the elastic loss. In most of these experiments, I'm going to be probing way off resonance, much lower frequency near DC, and these mechanical resonances are going to be way up at high frequency, right? So I'm looking at the tails of this mechanical resonance. And in this plot, I've shown 3 different mechanical quality factors, a low one, a medium one, and a very high quality factor, or flip that, let's say a large imaginary component of the Young's modulus going to a low value of the imaginary component. As I increase the mechanical quality factor, I'm going to start packing the motion into the resonance, right? So I'm bringing down the tails, but I'm packing the motion into the resonance there. If I integrate over all frequencies, I'm going to get the same value because that's just proportional to temperature. So I'm going to pick up motion on resonance, but I'm going to drop motion off resonance here. And let's go to the most extreme case. Let's just make up a system that has 0 elastic loss. It would have a delta function at its resonant frequencies and then no motion anywhere else, right? So if you come from an electronic materials background, I'm shaping the density of states for the phonons that live in the system. I'm shaping where mechanical motion can occur, in frequency realm. So as I reduce the elastic losses, I can bring down the tails, pack all the motion in around the resonances, and I can make it effectively quieter in the frequency range that I want to look at. So you can shape the Brownian noise response by choosing the right materials. So again, I hope you learned something from that. And what you have to keep in mind, I showed that expression earlier, which is the noise expression. It is the infinite series of all the mechanical resonances of that body. So there may be mechanical modes that strongly perturb the length of the cavity, and those will have a big impact, but there may be some mechanical modes that don't do anything to the cavity. They're still in there and they have a small contribution, but yeah, it'll be minimal. But you have to sum up all that infinite series of modes there, look at the off resonant contribution from each, and you have to minimize that for all of them. So you need to choose materials in your cavity that have the lowest elastic loss possible: substrates, spacer, and coatings, because coatings are the big limitation right now. So to put it in perspective, a ULE spacer will have a mechanical quality factor of a few 100,000. The substrates can have 10 million, tens of millions for good quality melt grown fused silica. And the coatings, an ion beam sputtered silica tantalum coating, will have a Q of about 2,000 or 3,000. It's a huge difference between a 50 million Q substrate or 10 million Q substrate. So the aim is to try to increase the mechanical quality factor, lower the elastic loss of the coating material. If you want to learn everything you've ever wanted to know about thermal noise and optical coatings, there is a textbook. I can share these slides, or I know this is being recorded, and I can point out this book. It's obviously everything you ever want to know about thermal noise and precision measurement. If we look at the cavity stabilized laser systems in more detail, I'll start going a little faster here. You basically take a pre-stabilized laser, so this kilohertz line width fiber laser, external cavity diode laser, or other, and we want to push it to even lower line width, even narrower line width. That laser intrinsically will have some shallow towns limited line width that's super narrow, but there's all kinds of external effects like temperature variations, acoustic noise, and so on that drive it to a wider line width. But I can bring it back to push it towards its quantum limited line width with a good servo system, with a good feedback system here. So I'm going to take that pre-stabilized laser, tap off some of the light, and put it incident on a reference, on an ultra stable, ultra quiet reference, right? And in that case, it's going to be my etalon that I showed earlier. I'm going to jump to this fractional frequency stability bullet point here. So the ultimate stability of that system is going to be limited by the length changes of that reference cavity. Let's say by the index perturbations in its volume, and then finally by the electronic noise in my feedback system here. If I use ULE, which has zero expansion, and I control the temperature, I can get rid of gross fluctuations of the cavity length. And if I put the thing in a vacuum chamber, I can take away any index perturbations in the cavity. And ideally, I build this thing up from this system up with low noise electronics. So I'm ultimately limited by the microscopic length fluctuations, which again is this Brownian noise issue that I showed earlier. To show why you see Brownian noise, these state-of-the-art laser systems show a delta F over F, or frequency instability, at the 1 part in 10 to the 16 level. So this is sub-hertz. You had many terahertz frequency. So you are looking at a length fluctuation on the order of 10 to the minus 17 meters in that system, right? That's deeply sub-proton radius. So you're looking at tiny fluctuations. That's why you see stuff like Brownian noise, in this case for a 10 centimeter long cavity. So we build these rather complex etalons. Another plug for Coastline that's helped us with the contacting and polishing and shaping in many of these. Room temperature systems are typically ULE spacers with few silica end mirrors, and we do cryogenic systems with silicon and sapphire. Typical mirror diameters are 1/2 inch, 1 inch, even up to 2 inch. Spacer lengths are from a few centimeters up to giant ones at 40 centimeters in length. These are usually at wavelengths at 1064, 1550, kind of these standard near infrared wavelengths, with the cryogenic systems going all the way down to liquid helium, 4K. As I mentioned, we can get the absorption and scatter down to the less than 3 part per million level in a good run, which means we can achieve reflectivities well in excess of 99.999%. So, linear cavities with finesse at the 300, 400, 500,000 in our optimized systems. I'm not going to go into more detail. I already went into a lot of detail on this, but these systems are phenomenal. You can make lasers now with line widths of 8 millihertz on the laser system, which means minutes of coherence time. Some of you have heard this if you've heard my talk before, but minutes of coherence time, like if you hit 8 minutes, that means your laser coherence length is 1 astronomical unit, right? It's from the Earth to the sun. So these are incredible laser systems. So you have to make an incredible etalon or incredible reference cavity for these lasers. We do commercial systems together with Menlo Systems. It's a company out of Munich, Germany, actually Martinsried, Germany. So we do these compact 5 centimeter cubic cavities or these long 12 centimeter cylindrical cavities. And they build these into a rack mounted cavity stabilized laser system. And we can now deliver commercial cavity stabilized lasers. Even there's a better plot if you go to their website now. There's an older one at the part in 10 to the 16 level, right? So these are cavity length stabilities at the sub 10 to my 17 meter per root hertz level, which is phenomenal. Right? These things are very still, very quiet cavities in a rack, which is quite impressive. So you're having an active vibration isolation platform, good temperature control, and so on. And it's really our crystalline coatings that can push these ultimate limits of stability over a fairly wide frequency range there. An exciting R&D area that we push into is expanding or scaling up the diameter of these coatings to do large area optics for LIGO. This is obviously the most stringent customer, lowest absorption possible, lowest scatter possible, but then even most challenging for us, large area, right? Right now, we can't even go beyond 20 centimeters due to the availability of gallium arsenide seed wafers. And they would like 35 centimeters, which is a major challenge. But we have demonstrated significant improvements in Brownian noise, which means that if you were to run a cryogenic system here, you'd have 10 times lower noise in the interferometer if you were to optimize everything else, to be clear. And the reach of these systems goes as the cube of the sensitivity enhancement. So you can increase the visible universe, the space over which you probe these gravitational waves by a factor of 1,000. Which means you can basically see the entire visible universe, or gravitational waves emanating from the entire visible universe with our coating. So clearly an exciting motivation to do that. Problem is capital equipment necessary to make large area semiconductor coatings is on the order of $20 to $30 million. So if anyone has a good philanthropic donation partner that will pony up $20 to $30 million, I will be very happy to talk to you about that. Here's an example of a 20 centimeter diameter, just test bond that we ran to demonstrate that we can do defect-free transfer at up to 20 centimeters. Again, that's not big enough for LIGO, but it's a step towards that to justify these sort of large investments. I'm now going to move on to the next topic, and this will be much shorter, which is showing the record low mid-infrared losses. Here the goal is to push to similar levels of performance to these like near infrared or ion beam sputtered optics, but in the mid IR for the first time. This is less mature than our near infrared products. I'll jump to the second bullet point there, but we've been making rapid progress. We've made prototype mirrors at 3.3, 3.7, 3.9, now 4.5 to 4.6 microns. These are very challenging to make because the crystal growth is very thick, and defect densities tend to get high, and so on. But the mid-IR is obviously a very interesting space to operate. You have all these very nice absorption lines that you can access to do trace gas detection and so on. You can do really interesting spectroscopy on carbon-based materials and among others. And so this is what we're initially targeting operation in the 3 to 5 micron range, making these long linear cavities for cavity ring down spectroscopy. For us, the key is to minimize background doping. So here's two theoretical plots for absorption as a function of mirror center wavelength. So I'm going to interpolate a bunch of different mirror designs, a bunch of Bragg mirror designs to make this curve. And you can see if I bring my background doping in the crystal down from something in the 10 to the 14 level to high 10 to the 13 per cubic centimeter, I can start to push these ultra low level, like ppm levels of losses out to very long wavelengths, sub 50 ppm, out to almost 10 microns. And it's very challenging to bring down the background doping in these semiconductors, but we're making rapid progress. So you can see I kind of put a blob over the near IR where we can readily achieve sort of 1 ppm and below. And then in the 3 to 4.5 micron space, we're making good progress here, staying below 10 parts per million there. And it's just working on the epitaxy, optimizing that to get just the purest intrinsic semiconductors possible. Already, some of our first prototype optics have been used in some very cool experiments. So this was a 3.7 micron linear cavity, about 1 meter in length. It was delivered to a customer in Gila in Boulder, Colorado. I'm not an atmospheric chemist, so I can't talk through this in detail, but basically they initiated some very interesting reaction between ozone and a deuterated, like equivalent of OH, it's OD in this case. And they were looking for the atmospheric intermediate HOCO. It's easier to measure the deuterated version, which is DOCO. So this material trans-DOCO, but they did a very cool real-time spectroscopy experiment where they put in the reactants, initiated the reaction with a UV pulse, and then measured directly all these fleeting intermediates that would, typically you write out a chemical equation and you have reactants and products, but there's a bunch of little dances going on in the middle there, and they wanted to directly measure this. They needed really high resolution narrow line width cavity, which means they needed their optical losses as low as possible. So hence our mirrors were very useful there. So very cool academic output. We use this to leverage and develop a new product line, which are crystal MIR mirrors, and we ended up winning a Prism Awards from SPIE and Photonics Media for that in 2017. This is the same gas-algas multi-layer material, but we transfer to a different substrate. Obviously, glass isn't going to work anymore out here. So we use things like single crystal silicon. More recently, some work on calcium fluoride, and there can be others. Yeah, basically just tailor the design of that Bragg mirror to work at these longer wavelengths. So obviously thicker quarter wave condition and so on. I'm going to jump ahead and just show, in the last couple of years, we made some prototype optics at 4.5 microns. These were measured by some partners in Vienna and by some partners at NIST in Gaithersburg. These are extremely challenging measurements to measure these ppm levels of loss. Here we push the transmission up in the optic to about 140 parts per million. We weren't sure what kind of excess losses we were going to get out here. We didn't want to be loss limited, but it turns out through careful measurements at the CDL in Vienna and at this group at NIST, we were able to tease out these very low levels of absorption, 7 parts per million. I'll make another plug for a company out of Hawaii called Stanford Photothermal Solutions. So they do this very interesting direct absorption systems using PCI or photothermal common path interferometer. Interferometry, and we worked with them to build a custom mid-infrared system to do these measurements. Also did cavity ring down, did some direct transmission measurements and so on in order to get this very high resolution measurements of the optical loss. If you're going to claim record levels of performance, you need to have good metrology to do it. But there's now the chance if we bring the transmission down, we could do enhancement cavities with a finesse well over 100,000 in the mid-IR. Current record finesse values at this wavelength range are 20, 30,000 kind of level. So now we're be able to exceed 100,000 with our low absorption optics. This is the final slide here. So, in summary, using this interesting combination of semiconductor materials and microfabrication techniques with bulk optics, we've realized a new premium optical coating technology, high performance in terms of low absorption, low scatter, and so on in the near IR. And now for the first time pushing it in the mid IR, very low Brownian noise, which you now hopefully understand. Feel free to ask me questions about that, which means you can make the world's most precise interferometers or most stable, quietest, whatever you want to say, interferometers. These materials have relatively high thermal conductivity, high CW damage threshold, and so on. And I will highlight one other point here. So far, we have solely leveraged the passive properties of these coatings, right? We've leveraged the fact that these are just low absorption multi-layers. But these are semiconductors, right? So they have active electro-optic effects. You could have gain, you could do photodetector on the mirror. There's all kinds of crazy stuff you could do, leveraging now the active aspect of the materials. I am looking for cool ideas there. We have not found, we've done some satchel absorption stuff and some other things, but you could do nonlinear light generation in these structures and so on. So just planting the seed there that there's, I think, a whole nother direction to go by implementing these semiconductors as transferred thin film structures. So with that, I'd like to stop and thank you very much for your attention. I'll click and open the chat, but if there's other questions that people want to ask in real time, please do. So again, thank you very much.
Thank you, Garrett. Okay, so we'll take the questions now.
Do you want me to go through some of the chat questions?
Yeah, go through the chat first, and then it may prompt them for other questions.
Yeah, so Mohammed had asked about have we produced curved optics? Yeah, sorry I didn't spend a lot of time on this, but that was one of the whole reasons to exist in the first place, was this ability to do curved optics. If you're going to make a linear resonator, at least one of the mirrors has to be curved to have a stable resonance. So typically we do 0.5 meter, 1 meter, a couple meter radii of curvature, but the tightest we've done is 10 centimeters, as I mentioned. So yes, we can do curved. I think that's a very important point to make clear. And point 2, are you concerned about delamination from the substrate over temperature? Yes. So these materials have relatively high coefficients of thermal expansion, about 6 parts per million, if you know these numbers. It's actually matched to sapphire, which is kind of interesting. So for fused silica, that's a huge mismatch because fused silica is sub ppm expansion. So yeah, we can operate at the room temperature, but with fused silica, for instance, we can't heat those optics above 150 Celsius or they start to delaminate. It depends on the materials combination. So YAG and sapphire are almost perfectly matched. We could heat that up until we degrade the gallium arsenide. But for things like glass or other materials, we have to be careful. Same with the cryogenic optics. We have to really optimize the bond strength. So when we cool those at cryogenic temperatures, we don't spontaneously have the coating fall off, which most customers aren't happy about their coatings falling off of their optic. And the next question was about cost. Cost is a bit unfortunate. So I showed briefly that catalog page from Thorlabs. We sell standard 1-inch optics at the 1064, 1550, and then there's a line at 1397, which is a strontium clock transition. Each optic is between $5,500 and $7,000 per mirror. So I know a couple people probably gasped or like tried to hide their wallet. That is very expensive for a single optic, but that's just the nature of what we do. It's challenging, crystal growth and microfab and all this, but we're aiming to bring this down. I will point out though, at volume, it should scale nicely. Production MBE chambers are large. We can deposit over a very large area. We can make hundreds or thousands of coatings, discs, depending on the diameter, and transfer to hundreds or thousands of substrates. At that point, you could bring the cost way down, right? Typically, we grow on smaller substrates in a big production system to pay for that whole crystal growth run. And if we make 4 optics, you got to pay for that whole growth run. So let's say again, right now, $5,000 to $7,000 per optic. If you want to go to high volume, I could probably push it to $1,000 per optic. That's the nature there. And I would say for those who have an ion beam sputtering background, somewhat comparable for custom run costs. But yeah, that should cover that. There was a question about, can you use piezoelectric effects for modulation? Yes. So you can do, gallium arsenide is an inherently ferroelectric material, so you can put a field on it and you can move it. We actually have customers who don't want that because we're trying to make ultra stable systems. So we have some recent measurements of stray electric fields and how they may perturb the cavity. I can provide numbers from that if somebody wants to email me. It's just gcole@thorlabs.com. Sure, that'll be shared. I don't know the numbers off the top of my head, but yeah, in principle, you can use piezoelectric effects to modulate the structure. Another question about how robust are these? Fairly robust. Again, we don't do other coatings, so I don't have a good comparison, but a properly bonded structure will survive a tape test and they don't degrade. They're not hygroscopic, so no water gets into these. Gallium arsenide based materials are pretty stable. Like I said, temperature can be a problem if it's a large mismatch with the substrate, but we usually tell customers what the bounds are. Like heat this optic to 150 only or below, or this one to 250 C and below, and so on. Atmospheric pressure changes doesn't seem to be any kind of problem. But yeah, moisture is not an issue. Most acids and bases on their own are not a problem. You need a mix of an oxidizer with an acid or a base. So they're pretty tough, at least compared to most mid-IR materials. And we'll throw out their surface hardness is comparable to, say, a silicon surface. So it's, yeah, they're fairly robust. It's not a soft material by any means. Next question about how long does it take to grow a crystalline coating? Yeah, so for doing the crystal growth, it's about a micron an hour is a good rule of thumb. So our typical near IR optics are our near IR HR coatings are about 5 microns thick, so call it 5 hours of deposition, whereas a mid IR coating might be 15 microns thick. So it's 20 microns. It's still less than 24 hours. So you're depositing over 15 to 20 hours roughly for one of these thicker coatings. So yeah, it's not a slow process. I think this is something I always fight with. People tend to think, oh, MBE is atomic layer by atomic layer, so it takes a month. No. It's like micron an hour. But then we have to do lithography and etching and contacting and blah, blah, blah. So it takes a lot longer, but the crystal growth process is relatively fast. I will provide the slides for sure. So I'll just mention that and jump to the next. Can I comment on the stress? Yeah, this was a bullet point. I know I covered a ton of information, but compressive stress 130 megapascals basically every day, because that is the interatomic mismatch between gallium arsenide and aluminum gallium arsenide. So slightly compressive, fairly low stress. Are they cleanable? Yes, all standard solvents, acetone, isopropanol, whatever detergent seem to be fine. Water, obviously. You can drag wipe them. You can use foam swabs. We have a cleaning document we send out. You can even use first contact if you know this gel stuff you put on and peel off. So standard cleaning. If anyone has more questions about that, just ask me. How We use a lot of layers because our index contrast is not huge. So again, high index, I'll exaggerate and say 3.5, low index 3. So our delta N is about a half. So for let's say a good example, 1064 nanometer HR coating with 10 ppm transmission would be about 71 in layer pairs, or 71 layers, sorry. So 35.5 layer pairs. That sounds crazy if you compare it to an ion beam sputter coating, but the total thickness is 5 microns. And the reason is that our refractive indices are so high. So when you have a high index of 3.5, your quarter wave condition is very narrow. It's only about 70 nanometers thick. And then your algas low index refractive index is about 3. So it's about 90 nanometers thickness. So the total stack is actually interestingly almost exactly the same as ion beam sputtered multilayer. So 5 microns around 1064 and up to 10 microns at say 1550 nanometers. 2 more questions popped up. So machine time for several micron growth, limiting factor at the coating price. It's not machine time. It is the crystal growth process. So Ken Bates is correct there. Like the main cost driver is epitaxy. So we take over that chamber, deposit or do crystal growth in it, and that's going to drive the cost. I think it's more maintenance on the machine, prep of the machine, filling it with the source materials and so on. And once you button up one of these MB machines, you don't want to open it for 6 months to a year. You want to keep it nice and seasoned and under high vacuum. So you're paying for all that. Kevin Romero asked, you have multiple HR regions over say 1 to 12 microns. In principle, yes. So it's an interference coating, so I can design AR coating, mid-level coating, HR coating. I can do all the tricks you do with interference coating to get what you want, whatever weird shape reflectance spectrum. Keep in mind though, as I mentioned, our refractive index contrast is not so large, which means it's tough to make, say, a steep filter. Like if I wanted someone with HR here and high transmission here and just a vertical line, that you really win if you have high index contrast. Like a good example system is silicon silica, which has a giant refractive index difference. Because ours isn't very severe, it takes a thick stack to tailor a certain reflectance spectrum. So I will warn you that on paper anything's possible, but I might do it design it on the computer and find out the stack has to be 200 microns thick. I can't grow that, and I can't make it. I don't have a cat next to me. Yeah, this is a good one. So Surge, I hope I pronounce that right. So why a flat on the coatings? So I should have mentioned this earlier and I forgot. So we add a flat to maintain the crystal orientation, so we know what the orientation of the stack is. Our materials are birefringent. So if you have an application that you cannot deal with birefringence, you don't want our coatings. This is really interesting because on paper, 100 gallium arsenide, which we use, has 0 birefringence. Even uniform strain should not cause birefringence, but we see birefringence. We're starting to narrow down where that's coming from. There's some sort of non-uniform strain relaxation after growth, and it is defined along certain crystalline axes. It's actually in this paper I alluded to. So we had a computational material scientist get to the bottom of that finally. So we think we understand what it is. It's funny, gallium arsenide is a well-studied material, but it's a weak birefringence. People hadn't seen it before, but we see it because our cavities are so narrow in terms of line width. So yeah, that flat in our optics is always on the slow axis. And I don't remember the orientation off the top of my head, so I don't want to say it, but yeah. So we always draw the flats. So when you make a linear cavity, you need to register the 2 flats to each other, and then you go in with a controlled linear polarization, depending on what you want. So that's something important to keep in mind in our coding. So thank you, Serge. That was a great question. And yeah, Kevin, yes, if I made that crazy 200 micron stack, it would take 200 hours. So I definitely don't want to do that. Yeah, that was cool. That was a lot of questions. So I've taken up a lot of your time. I apologize for those who wanted to get out early. But
Okay. Are there any other further questions? You can open your mic if you have.
yeah, and like I said, I'll share the slides and I'll feel free to
Okay.
distribute my email address, and I'm always happy to, to answer questions or reach out. So I hope somebody
Okay.
learned something new, found out there's a new coding technology, learned about Brownian noise, and now you can forget about it because you'll probably never deal with it again. But
All right. Thank you for a very interesting talk, Garrett.
Yep.
And so people can get in touch with you if they have further questions.
Yep. Yeah, definitely. No, thank you everyone for attending. I'm very impressed. I'll definitely have to do more of these OSSC meetings, watch the speakers and participate. And once we can start traveling, go down in person, it'd be nice to meet everybody.
So Gary, you'll be happy to know that having given our talk for us, you now get a free OSSC membership.
That's what I heard. Yeah.
You can just save the $15.
Yeah. And I think Mark White is also, Mark, as I mentioned, was our head of sales at Crystalline Mirror Solutions and continues to do OEM sales. And he is now a member too, I believe. Mark can confirm that for me. But
Yep, that's correct.
Yeah.
That's
again,
wonderful.
Should have joined a long time ago.
Yeah. Oh, yeah, we should have. I know. We were a cash-strapped startup. We had to save our tiny
$15.
Yeah.
Any way we can help. $15.
Yeah.
All right. Have a
So
great
we are
evening.
going to have a breakout room now, and we're gonna go talk about. We have some people offering positions and things like that. I was thinking we could have a general forum one as well, but I know that we planned the breakout room for job opportunities.
Okay.
If there's any interest in the general forum thing, we could build that up, but for sure we'll have the breakout room focused on open positions.
All right.
All right. I'm going to run to family here.
All
I'm
right.
actually on the road right now, but thank you guys. And sorry the
Thanks
internet kind
again.
of dropped out in a minute.
Okay.
Yeah. Bye.
Thank you so much, Garrett.
Yeah. Bye, everybody. Thank you. Bye.
Thank you, Garrett. Great talk.
Thank you. Bye.
Okay, so now we have one room open, which is the jobs and optics. And as you can see on your screen, we have engineering and sales managers from 3 of our large local companies, 26, MKS, and Octo Sigma. You can manually join the breakout room to talk about these companies and the positions that they have open using your window. And then otherwise, I will start putting people into the room.
Okay.
John, have we stopped the recording?
Oh, we need to do that.
So we will stop that, yes.